this recording? Yep. All right. So let's kill off some of these things so it doesn't kill my battery. All right, so were there any issues with the homework assignment? Any tricky parts to that second section? That should have been relatively easy, right? That's still kind of little tiny intro things where the book is more, the sections that I've assigned you so far for the book should be pretty much review from last semester, then filling in a couple of things that maybe we didn't discuss. Okay. So, we talked last time about some of the Boolean stuff. So remind me, what's a Boolean expression? Any expression that boils down to a single value of true or false. That was almost the quiz question. Speaking of the quiz question, 110, 111. Did you get that one? Oh, what'd you put down? 55. 110, 111. So this is the ones place, the twos place, the fours, the eights, the 16s, the 32. This is 32 plus 16 plus 4 plus 2 plus 1. So that's what, 48, 52, 54, 55. All right. So this is 1 times 1 plus 1 times 2 plus 1 times 4 plus 0 times 8 plus 1 times 16 plus 1 times 32. All right, questions about that? So we looked at that in class, and it was also from the book reading. In fact, I think they had you practice a bunch of them, right? Yeah. So something to look forward to, Tyler. Oh, great. Okay. So we talked about the different, well, we also talked about hex stuff, but I don't think the book talks about hex conversion, does it? Okay. So we talked about Boolean expressions, the Boolean operators we use, the arithmetic ones, as well as the logical Boolean operators for creating Boolean expressions. So the arithmetic ones are working with numbers, is 5 less than 7, that kind of stuff. The logical ones are from working with multiple Boolean expressions. You know, is it sunny outside and is it windy? That kind of stuff. So the ands and ors. Remind me, what's that guy, the little caret? What's that Boolean, logical Boolean operator for? I mentioned we won't use it. Not that you can't use it, but it's not a commonly used thing. But from a trivia knowledge perspective, anybody remember what that guy's for? This one right here. What's that Boolean operator? Exclusive OR, XOR. So exclusive OR is almost like a normal OR, except it's one or the other, but not both. So exclusive OR says exactly one side of the Boolean expression is true, not at least one side of the Boolean expression. Okay? You can build an exclusive OR using normal ands and ors, but so when you see this in some other classes, it's usually written as XOR. Or sometimes people call it XOR. I've never called it a XOR, but people do. All right, so that's what that guy is. And then what are these two? What's that guy? Bitwise and bitwise OR. Okay, how do bitwise guys work? If I take two values and I do a bitwise and on them, what am I actually doing? Okay, so I would take, if I had the number 5, for example, it would be 101. That's the number 5. 4's place, 2's place, 1's place, so 4 plus 1. So 101. I would compare 101, and let's just look at it. Did I give you an example of it last time? If not, let's just do it real quick. So 101 with, let's just do 1110. So if I was doing a bitwise and, I would compare this bit to this bit. All right, and since both of them need to be a 1 in order for the whole thing to be a 1, that would be a 0. This would be a 0. This would be a 1. So 1 and 1 is 1, 0 and 1 is 0, 1 and 0 is 0. So this would be the result of bitwise ANDing those guys together. It's used for completely different stuff. Okay, so that's why we don't really talk about it too much in here. We will talk about it in the computer architecture organization class. It's used for some other things. But for you guys, maybe from a trivia perspective, could show up as like an extra credit question or something like that. Kind of how do the bitwise guys work? Not so much what are they used for, since that's not a topic for this course. Let's call this bitwise example. Okay, so those are a logical Boolean. Oh, there was our example of the bitwise. So we got a couple of them there. We also talked about the left and right shift. Again, those would be extra credit type questions. So everything moves over to the left, or everything moves over to the right, and then we pad in zeros on either side. It allows you to like multiply or divide by powers of 2. It's kind of where it comes from. Not operator flips a Boolean, so not true is false, not false is true. All right, so then we started talking about the generic syntax for variables. So this is really kind of the last half of chapter 1 in the book, and then into chapter 2. So we have whatever the type is, followed by the variable name, followed by the value, and what are the different types we can use for variables in Java? What can fit in that type place there? I'm just asking you to read 2 lines down on the slide. Even you can handle that, Tyler, right? Seriously, well, you are a football player. You see that late hit of that Wisconsin guy the other day? Yeah, Wisconsin LSU. I guess Wisconsin intercepted it to basically solidify the game. It was a close game, and I don't know, this guy that was like the size of looked like a dump truck. So, and he was a big dude. Just blindsided the guy. He was already celebrating. I think the guy's okay. I'm surprised. I thought he was going to die. It looked pretty rough. Yeah, I mean, he was like a rag doll. So I can imagine you doing that, like unsportsmanlike type stuff. Yep, true. All right, so our types here can be any variable type. Now we have a nice little list of variable types that we've been talking about. So that first list is our primitive types. What are our primitive types again? That could have been today's quiz. That was almost today's quiz. Go ahead. So far, we're mostly good. You said long, Boolean, okay. Double, float. Okay, so he had said bit, so we have byte, short, int, long, char, float, double, Boolean, right? All right, so I tend to remember those by counting up from the smallest to the largest integer types. So byte, short, int, long, those are all signed integer types. What does it mean for an integer type to be signed? They can hold both negative and positive, so we take one of those bits that make up that guy to store that sign. So we get a little bit less total capacity. So an 8-bit byte only gives us numeric capacity in 7 of those bits. We only get to use 7 bits to. Oh, you're here again. That's like 3 for 3, right? I think it might be actually. Yeah, impressive. So congratulations, I suppose. We'll celebrate each attendance. Yeah, so we use 7 of those bits, so we actually only get 2 to the 7th power is the maximum size numeric value in a byte. because that eighth bit is used for the sign. Okay, that goes through short, int, long as well. All of those are signed values, so we have to take away one of the bytes. So a byte is an 8-bit, a short is 16, an int is 32, and a long is 64. All right, now what are chars? Tell me about chars. How many bits are chars? 16 bits, okay? And are they signed or unsigned? Unsigned, so we don't need to keep track of a positive or negative number. All right, so a 16-bit int now is a char is a 16-bit unsigned number instead of a character. When we think of chars, we think of characters like A, B, C, those things. Okay, why do we store chars as numbers? What's the purpose of that? So it's unsigned to begin with, so that means the smallest value is 0 that we can store inside of a char. What's the largest value we can store inside of a char? I don't necessarily expect you all to have memorized this. 16, well, okay, fair enough. Yeah, 16 ones would be correct. Do you know what number that is? 65,535. I just did the math in my head. I maybe have said that number a couple of times. Okay, 65,535. So we have 65,536 unique characters that we can represent. Now, what do I mean by characters that we can represent? How do those numbers turn into characters? Let me just show you something here real quick while we're at this. There's that number. 65,536 is 2 to the 16th power. So what's the, how do those numbers turn into characters? Unicode. Tell me about Unicode. Okay. So we basically have a list of all the characters. And next to that list of all the characters, we have a list of a bunch of numbers. And each one of those numbers maps to one of those characters, right? That's Unicode. What do we have before Unicode? ASCII. Okay. What was wrong with ASCII? Yeah. So it was really English only, and then like playing cards and smiley faces and that kind of stuff. Right? So once we decided that, the world has more languages than just English, and we had to create a larger character set. Now, is Unicode and ASCII completely different? Or are they pretty much the same thing, just stored in a larger address space? So ASCII is an 8-bit character mapping. So we have 256 unique characters in ASCII. The first 256 characters in Unicode is the ASCII character set. So while ASCII is 8-bit, Unicode is 16-bit. So we have that much larger of a unique, let's call it address space. So when I say 16 bits, 2 to the 16th unique things we can represent in Unicode. All right, so that's all 65,536 unique characters in the Unicode character set. So we have all sorts of symbols from different languages and things like that you need some of the special keyboards for. That was an interesting, it reminded me of he's still a student here. His name's Etma. And he was in my office last year, and he has a MacBook Pro, but his keyboard is all Arabic. And some of the keys are in weird places. So like I'm trying to type on it like it's an English keyboard, but some of the stuff is not in the same place. So yeah, it was a very interesting experience for me. I needed the Unicode mapping to use his laptop. All right, so our variable syntax types can be anything that we can create variables of. So we just talked about our primitive types. Now we do have a couple of object types. We started talking about those. Well, we've talked about those in class. We talked about them a little bit last semester, and your book has begun talking about those for some of you. So what's our current famous object type that we focus a lot on? Strings. Yeah, strings are very, very, very important in the Java language. All right, so I typically will say something like Java is a string-based language. So if we can get something into the format of a string, it's very malleable. So we can do things with it once it's in a string format. All right, so we're going to spend some time talking about strings today. All right, so conditionals, this is kind of what your second part of the Code Academy was, right? Dealing with if statements and that kind of stuff. So that should have been pretty straightforward, mostly Boolean expression practice. Fair enough? Okay, so really what we want to get out of conditionals is we go back to that original list of 3 things that I say, how do human beings solve problems? We remember stuff, that's variables. We ask questions, that's conditionals. And we do repetition, that's our loops. Okay, so we want to keep coming back to how does a programming language mimic the way we as humans already solve problems? Then it becomes less of a foreign exercise for us. Does that make sense? Because right off the bat, programming is going to be intimidating because we're using a different language. It's not going to be any different than what I just explained a few minutes ago, talking about using an Arabic keyboard. I'm very familiar with using keyboards, but the symbols on the keyboard were foreign to me. So once I would have learned Arabic, I could have used that keyboard. Okay, but it was an intimidating adventure for me since it looked like nothing to me, right? I don't understand the language. So that's kind of where we're at with Java. For most of us, it's a new thing. It looks weird. Why can't we just write it in English is the deal. It's actually a decent question. Why can't we just write our programs to tell a computer what to do in English? What's wrong with English? Or any natural language for that matter. Arabic, French, Japanese, German, pick your poison. What's wrong with natural languages in terms of trying to tell a computer what to do? So that's ultimately what we're doing with a programming language, right? We're learning all these gibberish things in order to tell a computer what to do. And right now it seems like it's a lot of work to tell a computer to do something very small. Like, what am I going to do with one if statement? Okay, so we're learning all these little puzzle pieces. We're learning about one Lego that we're going to then put together to build the giant Lego Star Wars Death Star. You've seen those at like the Lego stores? Well, I mean, I think they build stuff at some of those Lego stores you can't buy the kit for, though. But I think you're right. I think you can buy the Death Star thing. But like some people built some crazy stuff out of it. I think somebody built a house.
Yeah, I saw that.
Like they actually built like a house people lived in with Legos.
It was a guy from Tokyo, the British version.
Okay.
He built a house out of Legos.
I mean, that would be talk of the town. You live in a Lego house. Like, you think of it as like it's like maybe not like that. It probably really isn't very economical because like if you need to put like a new thing of drywall up in your normal house, you go to Home Depot and what's a drywall sheet, $12 or something. Not anything ridiculous. Well, I mean, to get the equivalent stack of Legos for a drywall sheet would be extremely expensive. It seems like it's like okay, I'll just take this entire aisle of Legos. It's like $600 in Legos to build. All right, so why are natural languages poor choices for telling a computer what to do? And this is really evidenced by kind of our trends in artificial intelligence, right? You see all these TV shows, and if you've taken the AI class here, where people are trying to tell a computer what to do, and they say something to the computer in English, right? And the robot sits there and sometimes acts appropriately, sometimes doesn't. It's something with the natural languages aren't translating well to a computer. Why do you suspect that is? Works for us. No guesses? All right.
Too complex to compile to assembly and then machine language.
Okay. Now the starting point should be you shouldn't have to guess. We need to talk about last semester. I expected all of you to study this heavily. Okay, so you say that English is too complex. All right, what do you mean by complex?
I don't know, I guess. Light bulb Java follow well as like a syntax. Like if you're going to take like the syntax of the natural language that humans speak, it's going to be way more. There's going to be way more options.
Okay. So how many of you have ever said something and somebody else took it the wrong way? All of us, right? Okay. We can even change it up based on facial expressions and stuff like that, right? So human beings talking to each other, there's a whole lot more to it than just the sounds that are coming out of our mouth. Okay, like you can tell whether somebody is sincere about what they're saying based on their facial expression, that kind of stuff, right? Okay, so English, or any of our natural languages, there's a whole bunch of little nuances that it takes a human being on the other side to kind of read between the lines, interpret what was actually said. Make sense? Okay, so English is a complex language. All of our natural languages are complex because human beings are complex. Computers are simple in comparison. They don't necessarily always feel simple to us because they're foreign. We're used to interacting with humans. We're not used to interacting with computers at the instruction level. So talking to the computer CPU isn't a comfortable thing for us yet. That's why programming seems kind of out there. But we don't need, well, not only do we not need, it's not an appropriate choice to use languages like English to talk to a computer because it leaves too much for interpretation. When we talk to a piece of digital equipment, a computer, zeros and ones, on or off, we need to talk to it discreetly, okay, unambiguously. Everything that we say can only be taken one way. That makes sense? English is not a good choice for that. All right, none of our natural languages are. So, in any case, that's why we have our programming languages, and that's why they have these stringent rules. Most of our languages are case sensitive. Let's call it high 90% of programming languages are case sensitive, which means that if you, like in Java, system.out.println, print something to the screen, the S in system must be capitalized. If you make it in lowercase, Java will scream at you. It's not right. Okay, you have to be completely explicit about what you're doing. It has to be accurate. Make sense? Which then means that you can write various lines of code in Java that are, from a syntax perspective, correct, but from a what problem are you solving perspective, completely incorrect. Okay? That's similar to human beings. If I go into McDonald's and I start placing a KFC order, okay, technically the words that are coming out of my mouth are going to be accurate English, right, for the person that they taking the order. But when I start ordering, an 8-piece chicken bucket or something like that, things are going to get funny pretty quickly is what's going to happen. Now, the challenge is going to be, what if the person at McDonald's tries to fulfill that order? They just act like, oh, they probably meant McNuggets. So now we have all sorts of interpretation issues, right? It's like, well, I wanted an original recipe. What's up with this? Okay, so in any case, English is a poor choice for that. We need languages like Java in order to specify these things. So when we talk about conditionals, what we're really talking about is how do we mimic the way human beings ask questions? How do we take the way that we would typically ask questions in English, take it down to a discrete, unambiguous level, give us a structure. In Java, it's called an if statement. Okay, so we have this structure that we have to follow, the word if, all lowercase, followed by an opening parenthesis, followed by something that fits the rules for a Boolean expression, followed by a closing parenthesis, followed by opening curly brace, list of statements, closing curly brace. I think I pointed out last time that technically the curly braces here are optional because the legal syntax for an if statement is if, open parenthesis, Boolean expression, close parenthesis, followed by a statement. That could be a single statement, single line statement, or if you have multiple statements to make, the statement you would choose would be the block statement, which is opening curly brace, followed by however many statements you want, followed by closing curly brace. So my argument is it's never wrong to use the curly braces, so I highly encourage you to always use the curly braces. And I probably mentioned that a modern language like Swift, a very new language, requires the curly braces. So maybe that's some evidence that they're kind of important, something like that. All right, but in any case, this little syntax here is all about us saying, how does Java mimic the way we ask questions in a structured, unambiguous way? Because in real life, when we ask a question, we're going to ask it, as if we're talking to a human who's going to be able to fill in the blanks, right? So if I'm at McDonald's and I'm trying to ask, if they have a certain, condiment or something like that, like, can you put the dressing that you put on the Big Macs on that thing? A human being will know what I'm talking about. That I want the Mac sauce, right? Okay, but a computer isn't going to be able to read between the lines like that. We need to be explicit. All right, so that's where, again, English is a poor choice. All right, so and then optionally we can have an else here. So we looked at some examples of that. All right, so now we transition into loops. So again, this is repetition. So this is mimicking. Is that how you spell mimicking? Seems like it's right. A couple more. That looks better. Mimicking the way humans repeat things. Autocorrect.
That's how you know mimicking is right.
You do, yeah, they didn't fix that. Yeah, most words like that, you could just keep adding G's to the end of it and it's fine. This is fine because you're all humans, right? You get that I'm joking and you know what that word actually means. Computer wouldn't. Got a little red underline. Hey, look, I haven't seen this word. And I've memorized the entire dictionary. Is what a computer is, right? So, more evidence. But I'm going to leave it because I think it's funny. All right, so in any case, so we have our loops. We have 3 different loops that we can choose from. We talked about these last semester. Anybody remember the 3 loops we have in Java? Okay, we have a for loop, while loop, DoWhile loop, okay? Technically, we also have a loop in Java called a for each loop, which at some point we'll look at, but let's just stick with those 3 starting points. So we have a for loop, a while loop, and a DoWhile loop. Now, in the world of loops, let's do it. We have pre-check loops. And we have post-check loops. Now, what do I mean when I say pre-check loops? What am I checking before? The Boolean expression. Okay, so we're taking this Boolean expression, that core that we've been talking about, any expression that boils down to a single value of true or false. We're taking that little piece. We can apply it to if statements where we're asking a single question and responding accordingly. We can also apply that same Boolean expression to loops where we're asking a question, based on the answer, we're doing something, and then spinning back up and we're asking that question again and potentially repeating the stuff again. In a pre-check loop, we ask that question before we execute the body of the loop even the first time. So a pre-check loop does not guarantee that we will ever execute the body of the loop. Make sense? Just like an if statement. So if you're asking the question, do I need to wear my coat? And it's negative 14 degrees outside. The answer should be yes. You should put a coat on, right? So you would, if it's negative 14, you would get a true out of that. You would put a coat on. With a loop, if you were saying I'm going to go outside to shovel, and you ask the question, is it too cold to shovel without a coat? Let's say, and my experience has been it's never too cold to shovel without a coat until you get out there and then you realize you're too cold, right? Same thing with scraping ice when you don't put gloves on. Like it's fine for like the first 15, 20 seconds. Then it's not fine, right? So our pre-check loops are going to ask that question before we ever go out there and start scraping, and then scrape some more, and then scrape some more. So if we think about repetition, what are we doing? Is the ice gone? No. Is the ice gone? No. Is the ice gone? Keep scraping over and over again. A pre-check loop is going to ask that question before we do it even one time. All right. So we have 2 of our 3 loops are pre-check loops. We have a for loop and a while loop. Both of these are pre-check loops. With that in mind, we can say that both of these loops solve problems similarly. Now, each one does lend itself to a certain kind of problem. So we might say that a for loop lends itself to counting problems. Maybe we expand that, where we know how many times we must repeat something. All right. So if we're making an omelet and we have 3 eggs, we're going to crack an egg, put it into the pan. Crack another egg, put it in the pan. Crack another egg, put it in the pan. We're done. We counted 3 times. We repeated something 3 times. That's a for loop. Okay, we knew how many times we were going to go into it. Okay. The alternative with a while loop, this guy lends itself to problems where we do not know how many times we need to repeat. All right, so keeping with our egg example, I might say, well, I'm going to keep cracking eggs and putting them into the pan until the pan overflows with egg. It's going to be a big omelet. Okay, so you crack the egg. Well, first of all, is the pan overflowed? It's a pre-check loop. I have an empty pan, not overflowed yet, right? Crack egg, put it in the pan. Is the pan overflowed? Nope. Crack egg, put it in the pan. Is the pan overflowed? Nope. Over and over and over again until I finally crack an egg, put it in the pan, get the drippings, spins back up. Is the pan overflowing? Yes. We're done. So we're going to keep doing it as long as the pan is not overflowing. That's when we're going to keep repeating. We don't know if that's going to take 19 eggs, 23 eggs, probably depends on the size of the pan, the size of the eggs, all that stuff, right? So we didn't know how many it was going to take. So those are kind of our problems that we can do with for loops and while loops. All right, and these are pre-check loops. So if we start off with a pan that's already overflowing, is the pan already overflowing? Yes. So we're not going to try to put any eggs in there, so we won't even put one more egg. We might need to go and transfer whatever we're trying to cook into a larger pan. Has that ever happened to you when you're cooking? Like you had this idea that stuff was going to fit in the pan you started with, and then as you kept adding crap, you realize that this doesn't fit? You just go big. Yeah, but then you don't get, but then it kind of can dry out, right? I mean, you need to have, it's got to be enough where you can keep all the sauces close enough where everything's getting, because if you get it all too spread out, then the sauce will just burn. You just add more sauce. So now you're back to the small pan problem, but in a big pan, so then you have leftovers, or in your case, just a big dinner. Yeah, no, I like your style. That's the first intelligent thing you've said today.
My first date with my girlfriend a couple years ago.
Yeah.
We went to Chancery, and the waitress comes at me out first. I ordered pizza, and she walked away. I was like, "No, that's just for me." She's the last one.
Yeah, we're not done yet. We're not close to done. Well, I can't do it anymore, but I think most of you are aware that I used to be a competitive eater.
I was not aware.
Oh, really? Yeah, so if you look me up on the internet, you could find all sorts of stuff with awesome fat. And yeah, I was on, I think 5 years ago, I was on Travel Channel doing a 10.5-pound prime rib at, so, yeah. So, so that's the... Yeah, that's the thing. Yeah. Yeah. And there's some older stuff, like when I used to do it professionally, I won the Alka-Seltzer US Open. This is like one of the major events in competitive eating. I did I did 17 pounds, 2.5 ounces of beef in one sitting. Yeah, it's a problem. So in any case, I can't do an 8 more. I can barely finish breakfast. But yeah, so I totally get your point of pretty much order one of everything. You can build all you can eat any place. Is what it comes down to. All right. So those are our pre-check loops. And let's look at syntax for these guys. So for a for loop, we have the word for, all lowercase, opening parenthesis. I'm just going to say counter here. We'll talk about that in a little bit more detail when we see an example of it. Followed by a semicolon, followed by a Boolean expression, followed by a semicolon, followed by change, counter, close parenthesis, opening, closing curly brace, statements. Same rule would apply here as it does for if statements, where technically you don't need the curly braces. It can be a single statement. Watch it later, Tyler. You pay attention to me right now. This is more important than how to fit 10 pounds of food into your stomach in a single sitting. I agree it's entertaining. Huh?
That's a debatable question.
I agree it's entertaining. But yeah, watch that later. There's some other things you should watch later too. I think I posted on Facebook this weekend. It was I think it was like Northern, the company that makes Northern toilet paper. Yeah, they have a like this funny commercial that they came out with. It's called it's like going back to old school, where the toilet paper is, hand pulped and hand perforated, and it's like basically wood. And they talk about how it's toilet paper you'll remember. It's not comfortable, right? Yeah, so it's really realistic the way they're showing these like artisans like in the wood shop making your toilet paper. It's truly tree to toilet, I think it said, or something like that. Yeah, so it's pretty funny. That's something else to watch later. All right. So syntax for a for loop. For, opening parenthesis, you initialize your counter you're going to be using for the loop, followed by a semicolon, followed by your Boolean expression, followed by a semicolon, followed by you're going to change your counter to some degree. A lot of times it's add 1 to I or something like that. We'll see some examples. And then you have your statements that you want to repeat as long as this Boolean expression continues to be true. As soon as that Boolean expression is false, we fall past the for loop and we continue on with life, whatever instructions come next. A while loop is while Boolean expression, opening curly brace, statements, closing curly brace. Now, at first glance, you might say, a while loop looks simpler than a for loop. There's not as many things there. But now the reality is, in order for us to create the logic that a while loop would require, we're probably going to need to have a counter or some sort of starting point that we'll have to initialize before the loop starts. We're probably going to have to change a counter or change some aspect of our logic inside of the while loop. So a lot of those parts are still going to be present. They're just not a required part of the syntax. And part of that is because for loops lend themselves to counting problems, so they're making the assumption, well, you're always going to need a variable to count, and you're always going to need to adjust that variable during the counting. So we're going to build it into the syntax. All right. Technically, you could leave this part blank, the semicolon still necessary, and you could omit this part as well. Okay, but all those semicolons are still needed. So you can actually initialize 0 or more counters there, and you can change 0 or more things here. All right, so there's some flexibility with how that statement works. Now, the connection I want us to start making as we're doing this, so one thing I'm kind of harping on here is this translation between how human beings solve problems and how computers solve problems, and especially as now we're going to be using Java heavily in this class as opposed to like last semester when we were using Alice, where it's a little bit more tangible. So I'll often make comparisons like if I went to Home Depot and I picked up the for loop tool, right? Sometimes you use all features of a tool. Sometimes you kind of use the generic way the tool works, something like that. But start thinking about these things as physical objects. That, oh, I need to repeat this 8 times. My go-to tool is a for loop for that. You go and take it out of the toolbox. Here's my for loop. I'll drop it into the, to wherever. I'll just put it there, and then I have to kind of set it up so it's ready to go. How many of you have ever played the game? I don't know if it's popular anymore, but it's a game called Mousetrap. You know of the game? Yeah, but so what are those machines called? There's a is it a Goldberg machine? Does that sound right? It doesn't sound horribly wrong, but I'm doubting it because it came from you. Yeah, but in any case, it's kind of a thing that I've seen at various like conferences and things like that. Some group of people set up some, we'll just refer to as a Goldberg machine. If it's wrong, it's his fault. But they basically set up this thing where there's a starting point and a whole bunch of maybe dissimilar things all have to happen together at certain times for, a golf ball to start off here and end up going here. And sometimes you have like boiling water here and the steam lifts a balloon up and the balloon then hits a spoon up here, which causes something else to start going. And you kind of know what I'm talking about here with these machines that all kind of link together. Think of programs as sort of like that. So we're kind of staging almost like a obstacle course, if you will, that we have to start from the beginning and we need to go through all these different parts of the course to ultimately get to an end goal. And sometimes you get some decision making. Sometimes you can go left and go through these obstacles. Sometimes you go right and go through these other obstacles. But the act of programming is kind of like setting up those obstacle courses. All right, you have to you have to set up all those little things in the middle that ultimately only let the right stuff come out on this end. All right. So, for instance, like how many of you are familiar with the Tough Mudder? Is that it's like an extreme obstacle course thing, right? Okay. So 2 years ago I did Tough Mudder. Well, okay, I almost did Tough Mudder. I was signed up for Tough Mudder. I was on a team, and then I hit the tailgate, where they tailgating, they cook out in the parking lot. Yeah, I never left that. So I cheered on my team from the tailgate with the food. Yeah. So I almost did the Tough Mudder, but I suspect I wouldn't have made it. That would be my strong suspicion. I probably would have found a nice comfortable spot in like a mud pit or something like that and just kind of chilled, would be my feeling. But in any case, so I wouldn't have been a positive result coming out of our Mousetrap. That was that. But as you're writing software, start thinking about things in terms of, these Goldberg machines where you're effectively setting up an obstacle course that all your logic needs to kind of plinko through, and in the end, you get something that comes out the other end. All right? So something to consider, maybe just almost a mental picture to create. Post-check loops. These guys check the Boolean expression after the body of the loop has executed once. Okay? Our DoWhile loop is an example of this. So syntax for DoWhile loop is do, opening curly brace, statements, closing curly brace, while, opening parenthesis, Boolean expression, closing parenthesis, semicolon. All right, so that's the syntax for a DoWhile loop. And this guy lends itself to problems where the body of the loop well, let's just say where something needs to happen at least one time. Okay? Now, the funny thing is that do-while loops are certainly in the wild going to be our rarest loops. But there are certain problems that pretty much require do-while loops. And I say pretty much with the caveat that you can technically accomplish any of our loops. Any problem that requires repetition, you could solve using any of the three loops with the right number of extra if statements and things like that to control the your Goldberg machine or whatever the right way. So, if you want to do it kind of a backwards way, you can. You just need to put some extra obstacles in there to make sure things happen in the right order. All right, so can you give me an example of a problem, a real-life problem where we need to do something at least one time? And the example I'm probably looking for is the one I gave you last semester. So we'll see if you come up with that. But any example that's appropriate for this is fine. I'm sure every one of you dealt with this today. Huh? You could potentially skip brushing your teeth, so that doesn't happen once. We hope that doesn't happen, but it's possible. Sometimes we're in a rush, right? We use pizza as a mouth rinse. It's like, well, bad breath or pizza breath. Let's go with pizza breath.
Did you use walking?
I didn't.
You used walking as an example for something.
It was day one of class, walking down the hall, not bumping into walls, all the things that we're doing, asking questions constantly, kind of how human beings solve problems. So how many of you did something on the computer today that required logging into something? Even if it automatically logged in for you. The authentication process still happened, right? Even if you didn't have to physically click the button. Okay, so when we're authenticating with a system, we have to provide a username and password at least once. And then if we screw it up, it's going to ask for it again. Make sense? So authentication would be an extremely common problem in the computer industry that would lend itself to a do-while loop. Go ahead and hit me with your username and password one time, and then I'll see if you got it right, and I'll possibly ask you more. Okay? So those are our three kind of loops. Now, in terms of, so just to put this in some context, I guess. What I don't want you to do is I don't want you to go home and just try to memorize all these syntaxes, because that's not the way to do it. The way to learn the syntax of an if statement or a while loop or a for loop is by practicing building while loops and for loops and if statements and those things. And over time, it will become second nature what the syntax is. That makes sense? So the way to learn programming is not to get this encyclopedic knowledge of all the syntaxes, because that's going to be useless, right? You can sit down and memorize. I think I probably have used the example like basketball, Michael Jordan. If you go and take his month-long boot camp, or you're ready for the NBA, something like that. You can go and read a book that talks about all the different basketball moves there are, all the different soccer moves there are, and you can memorize every single one of them. That doesn't mean you're going to go out and be a professional basketball player and be able to execute those things accurately, even though in your mind you maybe know, like, okay, this is how you shoot a jump shot. Well, there's all sorts of variables that are coming into play in real time. How tall is the defender in front of you? Are their arms up? Am I going to be able to shoot it past them? All this stuff, right? So just memorizing those moves doesn't really do anything for you, other than kind of give you extra knowledge of what you suck at, right? Maybe it's even worse. You take a video game, so let's take something like Call of Duty or something like that, a game I suck at, all right? So all the first-person shooters are just too fast for me. So when you take a game like that, if I were to give it the time of day, to try to get good at it, I suspect that once I learned 1 or 2 basic skills, you can probably leverage those basic skills against kind of a lower level of competition in those games, and that is probably good enough for a while. Until you want to go up to the next level of competition, then you got to learn things beyond those basic skills. That makes sense? And those things come with practice. You don't just read the instruction manual or watch a YouTube video on how to be awesome at Call of Duty and then sit down and do people still say pwn noobs? Is that not a thing anymore? We don't say that? That's a old World of Warcraft thing.
Blizzard.
Well, did it?
Blizzard did that.
Yeah. No, I still say it. So so I'm being laughed at behind the... Oh, I get it. It's disheartening, actually. Does anybody in here play World of Warcraft? Man, so that's like the old person game now, right? Is that it? It's all first-person shooters now?
I mean, I remember playing the free trial of World of Warcraft.
Free trial.
I was a kid. I didn't have money for a while.
Well, World of Warcraft just came out with a new expansion last week. Oh, you'd rather play the free games? No, I get it. But you still got to pay for the game up front. But you do with WoW too. You can do the free trial, but then you're going to eventually run out of content. So the problem is you can play a game like WoW for free until you can't. So why get addicted to something that you're going to end up having to pay for? You might as well get addicted to something that's a one-time, you pay your $60 and then just play it for zillions of hours. Yeah, that makes sense. It's a business model thing. What was it? Oh, so we were talking about Call of Duty, game that I'm good at World of Warcraft. So the punchline is that you take a game like Call of Duty, you can go and watch a YouTube video on how to be awesome at that game, right? And it's not going to make me sit down and be awesome at Call of Duty. I promise you. Okay, not that any of you suspected that might work, but programming is very similar to that. The only thing that's going to make you better at programming is sitting down and programming and not overreaching. Starting off with simple things, even though it's kind of boring, you're like, oh, well, shouldn't I be able to write video games? Eventually. Okay? Eventually, you'll take these simple skills you're learning today, you know, those 1 or 2 basic skills from Call of Duty, and those will be part of the skills that you use if you're playing, you know, these esports, you know, professional level Call of Duty tournaments and stuff like that. You still use the basic stuff, but then you have, you know, more advanced moves and knowledge of the maps and blind spots that you learn on the map, you know, all sorts of things that only comes from experience. That makes sense? So most of us in here can relate to that example because many of you have played video games, or you can take that example and extrapolate it and put it to something else that you've done in your life. Take that back and say programming is likely like that. That's when I say something like programming is like a sport, or programming is like becoming good at a video game, because now those lines have become blurred. What's a sport? What's not a sport, right? So sitting down and memorizing syntax is not going to get you anywhere. You're going to learn the syntax. You're going to memorize what an if statement looks like, what a for loop looks like, all that stuff by doing it, not by just cramming for an exam or something. All right, so it's you know, if you cram all the basketball moves and you got to go and do one-on-one against even an old Kobe Bryant or something, it's not going to go well. So you've got to get really good at basketball first and then play against a less good basketball player. All right, so questions about any of that? Kind of throwing this all into context. And really what I wanted to get out of that is how to study. The way to study programming is not to sit down and memorize stuff. The only way you can do it is swap hours for knowledge. And I get it that when you have real lives, like going to your football games and not having internet and all that stuff, you want everything to be cut and dry. Well, computer programming isn't that. Now, the good news is once you become good at computer programming, your lifestyle can be pretty decent. You can make pretty good money doing things that other people really can't do. it's a difficult task. That doesn't mean that programming is like, better than something else. I mean, heart surgery is very difficult as well, and I don't want the guy who just read the book on heart surgery to be performing my first triple bypass, right? You kind of want the guy who's done a couple. It's one of those things you don't cut corners on. Isn't that funny with like economy? If you go to like the grocery store, you'll buy the generic milk instead of the, to save 30 cents. But we wouldn't do that for heart surgery. Well,
nobody wants to have their first heart surgery.
He's got to have that first one, right? It's got to be like a pro bono thing where, it's like somebody they don't have insurance so there's like, look, it's not going to get done otherwise. This guy's had all the training. He's good to go. He's ready. He's done this on 50 cadavers. Okay, 100% success rate. Yeah, he actually saved a guy. He'd been dead for a decade. Brought him back. That's how good this surgeon is. Yeah, nobody shops around for. Well, I mean, I think people do shop around for the talent, not for the price for heart surgery. But people do shop around now. It's like in the health industry, it's kind of a new technology meets health. So how many of you have ever had an MRI done, for example? Okay, so football, you certainly would have concussion stuff. Yeah. So typically, if you go to your doctor and your doctor says you need an MRI, you go down the hall to that same facility and get your MRI, right? And it costs what it costs. You don't think about it. Well, MRIs are not the same price at all the different places. So there's some new apps and stuff out there where you can shop around for MRIs relative to what your insurance will pay for and stuff. And I mean, sometimes it's like ridiculous. I mean, that's just the one example I've seen. But like, I think like some places will charge, your out of pocket will end up being the difference between, let's say, $200 and like $10 for shopping around an MRI. No, I get it. I mean, I get it, but there's that level of convenience with health insurance, and then there's like, well, you wouldn't just close your eyes and grab an orange at the grocery store. You'd probably look for one that doesn't look obviously rotten. Just kind of interesting stuff how technology can get applied to all these different things that as human beings, though that information is not readily available to us. We're sitting in the doctor's office in the one size fits all medium gown. They're saying you need an MRI. You're just like, well, let me get out my smartphone. Let me shop around, see who has the cheapest MRI. That's not like, first thing on your list, especially when you have a concussion. You're not really thinking straight. Well, I mean, you don't really think straight most of the time. Have you had an MRI this week?
No. I had 5 last.
That kind of explains some stuff.
I got a concussion when I was in study. They paid me like $60 for
Okay, so you got one concussion?
Yeah.
Okay.
They were doing a study to like see how your brain develops after it was like.
Or doesn't develop for.
Well, yeah, or just it was like the day after that.
I get it. So they were trying to gather information. It's all part of the whole long-term effects on concussions on football players, right? Well, don't you need to practice? I mean, it comes right back to what we're talking about here. How are you going to become a better football player if you don't go to practice? You can't just watch the tapes. Not with your level of talent.
At this point, the coach is just giving up. Like, no matter how much practice, it's not going to matter.
This guy's not going NFL. Okay, you're going pro in shot put or rock throwing. Or you're shot put, right? All right. That's not healthy. Trust me. I'm sure that thing took years and years off my life. But I got some good videos to show for it. So you win some, you lose some, I suppose. Okay, so that's kind of our dealio with loops. Let me fly back here into. Okay, so we are technically supposed to be done with chapter 3 of the book, or are you chapter 2? 2. Okay, so you're through this part. So we just talked about, oh, so you haven't even done if statements. You've done Boolean expressions, the book. Okay, so let's think about this.
Code Academy had us do if and switches as well.
Yeah. So we're a little bit ahead on Code Academy, right? All right, so let's, for next class, let's do chapter 3 from the book and expect a quiz. And let's pause on Code Academy for right now to catch up from the book. Does that sound like an appropriate amount of one chapter from the book instead of 2 chapters plus Code Academy? Is that kind of a right size for 2 days? You have no idea. Yeah. So those of you who haven't done anything from the book, I will expect you to catch up and do everything from the book, right? See, now, if you had told me that you don't have Wi-Fi here, but you had Wi-Fi at the hotel, I would believe that. Because I tell you what, I have a tough time watching Netflix in my office. The only way I can do it is on the guest network, the guest Wi-Fi network, and then that cuts out half the time.
I did a speed test. There's such a big difference between Wi-Fi and directed in, like more than you expect.
But you also can't just look at, I mean, that's also going to be situational and what's going on in the rest of the network. I mean, so I think we've probably talked about this in one of the classes you've had with me before. Here on campus, we don't just inherently have bad internet. We have good quality internet here. There's just a lot of problems that a campus network has to solve. And those tend to be a quality of service issue for different demographics, right? So most of the time, people don't have issues printing on campus because that stuff has to work in terms of what the goals are of our network. But you might have problems connecting to Call of Duty, the live service for Call of Duty or something like that because of some of these it's called QoS, quality of service flags we have set up. All right, so for next class, make it through chapter 3 in the book. Wherever you currently are in the book, get through chapter 3, completing all the exercises, and be prepared for a quiz at the beginning of class on Thursday. Sound good? All right, I will see everybody on Thursday.